this disclaimer, and I need to do this constantly with you as we go through this and study this. I am not telling you that I am endorsing anybody that I quote. I am not telling you that I necessarily agree with everything that I give you. What I am trying to do is to lay this out before you for you to consider and think about, because there are a lot of possibilities going on here, and we need to be informed. And informed people are armed. Ignorance is very expensive, and my people are destroyed for lack of knowledge, he said in the book of Hosea. So I may give you some hypothetical situations that seem wild and unplausible, but I want you to think about these things, because some of the stuff that I give you is going to come from some of the most brilliant minds on this earth. So Stephen Hawking says plainly that what's going on in Cern could destroy the universe. Well, what is going on in Cern? And I want to read some of the statements that come from these people. And here's what one says. Sergio Bertolucci, the director of the Research and Scientific Computing at Cern, here's what he says. The Large Hadron Collider, and that's that thing that is 17 miles in circumference, about 300 feet beneath the surface of the Earth, the Large Hadron Collider could open a doorway to an extra dimension, and out of this door might come something, or we might send something through it. Now, of course, that begs the question, what do you expect to come out of that door, or what would you send through that door? And the bottom line, he doesn't have a clue, because he's in the area that is unknown, and he's venturing out into the unknown to try to do. This is why Stephen Hawking is so alarmed. It's for the simple reason that he understands, to try to put it in layman's terminology, they're messing with something that they cannot control, and they may open Pandora's box, and when they do it, they won't be able to put this creature back in the box. Now,
I believe that humanity is on the cusp of the most important technological, societal revolution that's ever occurred. And that's when we got to the point where the machines that we build outpace us in every respect. I don't mean that they're better calculators. I don't mean that they're better at searching. I mean everything. And I think that we're very close. And my prediction is that within 15 years, we will have machines that outpace humans in everything. Thank you very much. Steve Jurvetson has been a longtime friend and investor in the company, and for those of you who don't know him, he's a Silicon Valley investor who's probably the smartest VC that I know of, and certainly the one that's the most attuned to technological trends. He's on the board of SpaceX, Tesla, Synthetic Genomics, which is Craig Venter's company that's trying to build artificial life, and Dwave, and that's it. And this is his particularly poetic way of framing the difference between the machines we build and conventional computers. This is what they look like. There are two of them. These are from our lab in Burnaby in British Columbia. From the outside, they look like giant black monoliths, big metal boxes, about 10 feet on a side, 12 feet tall. And they are powered, they have a fridge inside them, a refrigerator that cools these chips to almost absolute zero. Just a wisp, a fraction of a degree above absolute zero. Hundreds of times colder than interstellar space. Amongst the coldest and most isolated and extreme conditions that humans have ever been able to engineer. These fridges, interestingly enough, which are called pulse tube dilution refrigerators, have a thing called a pulse tube, which emits a sound roughly once per second, which sounds eerily like a heartbeat. So if you have the opportunity to stand next to one of these machines, it is an awe-inspiring thing, at least for me. It feels like an altar to an alien god. They really are impressive machines. So imagine a world where all of the laws of physics as we know them are obeyed, but different decisions were made along the way. Different decisions at the level of tiny microscopic particles, different decisions all the way up to what you chose to eat for lunch, and whether you chose to come to this session or not. Quantum mechanics makes a very specific prediction that all of those are as real as the thing that you remember. And this is bizarre, because we don't see those other things. But science has reached the point now where we can build machines that exploit those other worlds. And quantum computers are perhaps the most exciting of all of these that we have within, or almost within our grasp right now. So these types of computers now are being thought of in the same way. They're not terrifically powerful yet, but they're doing something completely different than what your computer does. And that thing is like flight. It gives these computers access to these new resources, maybe you could call them parallel universes, in order to do something that you couldn't otherwise do. And that's not the only one. In fact, the one I'm going to come back to and talk to in the context of the story that I'm wrapping this in was recently installed at NASA. And Google was the primary interested party that pulled this whole thing together. And this one is really exciting to me, because what they're going to do is apply this machine to an area that I think is fundamentally important. It's a crux of our future as humans, and that's, can we build machines like us? So building machines like us might be possible. I certainly believe it is. I might be wrong. But what I do know is that the types of approaches that people are taking now to build intelligent machines benefit immensely from what this machine that we've built does best. So what this center is about is applying this beautiful new computational idea in the service of trying to make intelligent machines. Now, I can't think of anything personally any cooler than trying to use quantum computers to build intelligent machines, so this is very exciting to me.
And I was trying to demonstrate the fact that digital cameras, there's lens flares, there's a whole number of different artifacts that can turn up, errors basically, when you're converting that photons into a digital image. And just your thoughts for some of the listeners out there, because this is a common thing, and because we had mentioned it as well, these skylines, your thoughts on all that kind of stuff, Tony?
Yeah, a couple of the emails that you and I traded earlier in the week was related to what appears to be sort of like the Truman Show, the movie in which he suddenly realizes that there's a dome, an artificial dome, a construct, a matrix over his head, and he's living within this matrix. And that, you know, is related to this whole discussion of we are living in a quantum computer, that we are a construct of a quantum program. And because of the aerosolized spray and the chemtrails and the heavy metals, they have been building this Truman grid pattern around the world. Now, we've talked about the sentient world simulation and in silico and in silicon in computer simulation run by D-Wave's quantum computers, but I'm talking about outside the computer environment, in which what we are surrounded in, what's being picked up by on these digital cameras and even night vision goggles and this sort of thing, may in fact be an artificial grid pattern in the atmosphere that's been constructed because of all of this terraforming of the atmosphere. And we are seeing hints of it and glimpses of it because purposefully it reinforces the narrative that we are nothing more than a quantum simulation within a quantum computer. So that's my take on it. Yeah, I think, you know, the fear mongering isn't necessary. I think that if just a critical analysis and rational presentation of what appears to be evidence, what appears to be factual. Just present it. Just don't, try to scare the hell out of people. It's not necessary. Again, I'll say that we're seeing these glimpses of a grid pattern in the atmosphere. Think of it in psychological terms, because I always tend to default to the psychology of things, and that is that if you show people hints of the evidence, you don't show them the whole thing. You just show them a little bit, and they go, ooh, that's what they've been talking about. They've been talking about we're living in a matrix, and there's some evidence of it. And then eventually they show the whole thing. They show the whole matrix in order. We're just geeks. We enjoy this stuff. And I got to tell you, the presentation we were watching was one of the lead scientists from D-Wave doing a presentation at Cern. Now, I want to reinforce that because I have said for years that D-Wave and Cern are interchangeable, that they're in bed with each other. And just the fact that this presentation, which was on the Cern archive server, and this was just about a week and a half ago that this presentation was made, shows that they are working together. And in fact, in the presentation, they were talking about the Higgs boson, the God particle, and the fact that D-Wave's computer can sort through the data that's generated from the collisions much more efficiently than any of the standard transistor-based computers, the supercomputers that they have as servers, racks and racks of servers at Cern, 100,000 servers there, as well as distributing through the ESNet5, the Energy Sciences Network 5 system, to over 160 laboratories around the world. The data generated from collisions is analyzed, and even at that, it takes them 6 months to confirm, well, to a 75% probability, confirm the Higgs boson. It took them 6 months to do that after the collisions took place. Well, that's a factor of, there's only about 1 in a trillion occurrences of the Higgs boson, if it actually is there. But I digress. The point here is Cern is tied to D-Wave, and D-Wave is analyzing the data and will be responsible for the portal.
At the heart of this
the presentation
big
today
box
was,
is a
hey,
tiny chip
we can
about the
sort
size
out
of
the
your
data
thumbnail.
and confirm that Higgs
And on
boson
this
for you a
chip
lot
resides
faster than
all
your
of the wonder and
mainstream
magic that makes
transistor
this
gate
thing go.
model computers, and that's where we're going today.
I'm not going to
talk
describe in
about
any
AI
mathematical
today.
detail how it all works, but let me give you an analogy. In quantum mechanics, there's this concept that a thing can exist in two states which are mutually exclusive at the same time, quote unquote. And I'm using those words because the English language was developed before we had concepts to describe what these things actually are doing. But I'm going to give you a roundabout way of understanding this. Imagine that there really are parallel universes out there, and now imagine you have two that are exactly identical in every respect, all the way out to the horizon as far as we can see, down to the last little atomic detail of every single thing, with only one difference. And that's the value of a little thing called a qubit on this chip, which is a contraction of quantum bit. And that qubit is very much like a bit or a transistor in a conventional computer. It has two distinct physical states, which we call 0 and 1 for bit. In a conventional computer, these are mutually exclusive. That device is either one or the other and never anything else. In a quantum computer, that device can be in this strange situation where these two parallel universes have a nexus, a point in space where they overlap. And when you increase the number of these devices, every time you add one of these qubits, you double the number of these parallel universes that you have access to, until such time when you get to a chip like this, which is about 500 of these bits, you have something like 2 to the 500th power of these guys living in that chip. So the way I think about it is that the shadows of these parallel worlds overlap with ours. And if we're smart enough, we can dive into them and grab their resources and pull them back into ours to make an effect in our world. Now, this may sound very odd to you and bizarre, and in fact, I am using language that a normal theoretical physicist probably wouldn't use, but this is, what I'm telling you is absolutely correct and in line with the way that these things actually work.
For those of you that understand quantum computing, and I know a lot of you that are listening do understand it, as I said earlier, we're talking about a paradigm shift in quantum computing. D-Wave announced in this presentation to Cern that they have a new generation of quantum computer. And I'm going to release to you today, and I think we're the first ones to break it, because they haven't even, D-Wave has not even published their paper on that, which is coming out later this year. Their paper announcing this paradigm shift to a new generation of quantum computers, still using qubits. But I'm going to describe for you the name of that system. How it operates is it's called sampling. Now, we have talked a long time about optimization, combinatorial optimization, and quantum annealing and quantum tunneling. Optimization, in short, is how they take all of the probable solutions, insert them into parallel dimensions, and retrieve multiple solutions. Well, that's the key. It is now a shift from optimization to sampling. So if you're taking notes, optimization is the old system at D-Wave with their old computers, even the 2000Q that was just sold to Temporal Defense Systems. And Kev, I'll let you jump in and give the names of the other companies with the 2000 model. But the point here is they're moving from optimization, pardon me, to sampling. And I'll break that down and I'll give you an explanation of why sampling is so important to our world, our everyday living. And it moves from sampling into working as a classifier of information. So we're going to talk about the new machine, but not until we come back from the next break, because I really want to set this thing up. Kev, go ahead and talk about the companies that now have the 2000Q besides Temporal Defense Systems.
Yeah, because that's kind of something we missed, and I certainly didn't comprehend that when we heard that Temporal Defense Systems, this encryption company, cybersecurity company, had bought the new model, the 2000Q, which is a 2048. I didn't appreciate the fact that everyone who had the other model, the older model now, was it the 2000X, Tony?
The 1000.
1000? Well, what the companies actually chose to do was swap out their chips. They basically had an upgrade. And the companies that chose to do that, I mean, some of them include Google, NASA, USRA, and even Lockheed Martin, to name but a few. Now, you've got this other company, Temporal Defense Systems. They've got one. And the thing that also struck me today in this presentation was the fact that the amount of unknown companies, and we've got universities as well, that are accessing the quantum cloud. They can actually use the quantum processing power of D-Wave via remote locations. It's amazing stuff, and it really does beg the question, Tony, as to, well, we know where they're going. We'll be going with that after the break, but it just shows you it's really out there in the real world now. We've got Virginia Tech. They're using it there in association with DARPA, no less, and other U.S. intelligence agencies. So here we have a direct connection between D-Wave and the spooks. And of course, Eric Ladzinski, the brain behind it, he came from a DARPA-funded project in the first place. It's got money, the money's coming out their ears, and I think you'll probably have details there of this latest round of funding that they've secured.
Yeah, they just acquired or were provided an initial 30 million with another 20 million coming if they meet certain criteria, certain benchmarks. But overall, $50 million from a pension fund in Canada that is investing in this Canadian company. This is Burnaby, British Columbia, D-Wave's headquarters. And so the largest pension fund administrator or investment group in Canada is investing in their own people in D-Wave to the tune of $50 million. They'll be building a new facility. And that facility is going to house the new computer manufacturing equipment that I'm going to present to you today. After this first break, I'm going to give you the name of that. I'm also going to go ahead and tell you something right up front as we go into the break. And that is that academic circles, research circles, as well as major computer companies that are traditionally involved with transistors have been pushing for what they consider to be the ultimate, and that is what they call the universal processor, the universal machine, the end all. Well, that's not the right target. And D-Wave has a different target. But here's the point. At the very end of this hour-and-a-half presentation at Cern made by D-Wave, one of their lead scientists presenting this material, the very last sentence that he put out there, and I think when we come back from the break, Kev will play that for us. The very last sentence was that he revealed that they have a prototype universal computer, but they are not going to sell it. They are not going to release it to the public.
We've been doing this for some time now. In fact, we have our own version of Moore's Law.
And I'm going to tell you after the break why that is so important.
The number of these qubits on the chip has happened once a year for the past 9 years.
Configured
So
computer.
for the last 9 years, every year,
And
the
we'll
number
define
of
what
these
it means
qubit
to be a
devices has
universal
doubled, and it will
computer.
continue to do so. As a point of reference, in terms of how fast these things are, in one generation of chip, the one from the system that was installed at USC to the one that Google and NASA have now, the speed of the device went up by almost 500,000. This is the kind of progress that you're going to see with these types of machines going forward. And 500,000 sounds like an abstract number, but I put up a little mental comparison here to see what 5,000 really means. 500,000 is a big number when it comes to speed.
But what they are more involved in is selling computers for which there is a market, a commercial market. That's why they are staying within this progression of up to now 2000, which is really 2048 qubit chipset, because there's a market for it. I guess we can't blame them for that, can we, Kev?
No, definitely not. And I think we'll just leave this scientist with the last words. Take us out to break. Take a listen to this.
Yeah, that's an interesting question. So I think one of the things we are doing is more and more hybrid use of quantum resources in conjunction with classical, because it's not going to be the case that quantum computer comes into the world and it displaces all classical computers. That's just not going to happen, right? But there are niche applications where the quantum is the right tool, and niche applications where maybe genetic algorithms are the right tool or something. I think there's potential for hybridizing in things like evolutionary computing and genetic algorithms. I don't believe anyone's done that yet, but I do think there's potential for doing that, yeah. And differential evolution, things like that too.
And I'm going to give you the name of the new computer system that D-Wave is coming out with. And they will, as I said, publish a paper to this effect later on this year, and would certainly, Kev and I will break that paper out to you as soon as it becomes public. This is called the Quantum Boltzmann machine. That's BOLTZMANN. So if you just go to Wikipedia, you'll see this. It's no big deal. I mean, in terms of, I'm not saying anything that's super secret. It simply means that they're taking the Boltzmann machine system and applying it to quantum computing. We are moving to sampling and classifications, a classifier system of information sampling. Now, I'm going to make this tangible. When we use our brains and our senses, we are sampling our environment. We are not taking in definitive answers. We're taking in all of our sensory inputs, and we're putting values to those inputs. We're sort of balancing things out. We're making a collage of our sensory inputs, which are all information. And if you will, it's all digital information. It's actually quantum information. Our brain is a literal quantum computer. The issue here is that D-Wave up to this point has been processing information in a classical fashion using non-classical devices known as qubits, quantum bits. And it's kind of like you're working apples and oranges against each other. And they've been trying to solve problems utilizing combinatorial optimization through a process known as quantum annealing. All right? The basic is that they're trying to find the lowest energy state in a quantum environment, which is made up of peaks and valleys. And in the valleys, at the lowest point, is the lowest energy state. That's where they derive the solutions from. But now the solutions are not so much as you would derive using a classical transistor-based gate model computer running in parallel, which is what the supercomputers do that use transistors. They all run in parallel. This is moving away from parallel architecture and linear processing and single solution results, which is what optimization is all about, was basically arriving at one solution with a early generation, even up to the 2000Q just sold by D-Wave. They're moving to the Boltzmann architecture, which means you can sample, like our brain does, all of the probable solutions and not necessarily agree on one specific solution. What they're doing is saying, we're going to take all of the probable solutions and weigh them out. They're going to classify those solutions. They're going to use that in a more holistic fashion, is the way that I would call it. All of those probable solutions. And to what purpose? Kev, I'm going to test you. Why would you do sampling instead of single solution processing? Why would you take everything in and kind of weigh it out and classify it out and sift it out and try to balance it out instead of just going after one answer? What would be the application for sampling, rather, if it operates like our brains? Why would you want a computer that operates like our brain? What do you think?
Why would we want a computer that operates like our brain?
Yeah, why would you want it to be sampling instead of operating like a transistor supercomputer that only arrives at one solution?
Because it's doing everything all at once.
Just like our brain does.
Exactly.
So this is artificial intelligence. This is deep machine learning, but it is a complete departure from the previous methodology of teaching machines. And this is why this is so impactful on our daily lives, because our phones, we're going to the Internet of everything. Everything is going to artificial intelligence of varying degrees of different levels of sophistication. Your phone is kind of like, chisel and stone artificial intelligence. And then you can ramp it up to, laboratory-based, particle physics-based supercomputer AI if you want. But there are a lot of levels in between that and a lot of different applications at different levels of AI. You can't just say AI is everything. It's different levels of sophistication or complexity of AI. But how do you teach a computer? Well, what's been done to date has been force-feeding computers, is the way I translate it. And that's what I do. I take the complex science and translate it into our own everyday language. What they used was what was called a feed-forward neural network. Basically, picture, let me put it this way. This sounds really bizarre. You know what furnace filters look like? You know, the filters you stick in your home heating system, your central air and heating system. You have filters, filter screens. Well, you put up a series of these screens all in a row, and you start at one end and you shove data through it, and it filters and screens it out until finally at the very end, after the last filter, you have a solution. That's why I call it force feeding. That's what supercomputers do. That's how neural network deep machine learning is done today. Where we're going with D-Wave is an entirely different system. It is holistic. It is taking all of the data in a Boltzmann configuration. And for those of you that are not looking at graphics of the Boltzmann machine, you probably recognize in your own mind what the Kabbalah tree looks like, the tree of life, what that looks like. This is similar to a tree of life in that you have circles and interconnections. And I believe that this is their cue at D-Wave, is that, like we've talked about, their use of Enochian mathematics and the Enochian alphabet and the language and communicating with fallen angels. Remember, this is a Christian show. We're not talking New Age. We're not talking occult practices. We're shedding light on those practices. What I'm saying is that the presentation that both Kev and I watched today, coming out of Cern, presented by D-Wave, just confirmed everything that I said to you. And that
So it was
is
occult
that
knowledge.
they're
Then,
undisclosed,
decades later,
will not be
before
released to
the
the
boom of
commercial
all
or
this
public
technology was
sector.
upon us,
Ultimate
If you look at a world
computer,
where
the
we have these
universal
chips
prototype they
that are
call it,
connected to the
is in
internet,
fact my
all of
600
a sudden,
self-tetrahedron,
every piece of
as I have
information
been
on the
saying for
internet
years.
becomes accessible to our minds.
user data online. Everything we buy, everyone we interact with, every opinion we share, every time we click like on something. This creates a codified version of ourselves.
When we use contemporary technology, a trail of information is created in the form of data. When analyzed, it describes our actions, decisions, preferences, movement, and relationships. This codified version of who we are becomes ever more complex, developing, changing, and deforming based on our actions. In this regard, this ledger of our data may be considered a Lamarckian epigenome, a constantly evolving representation of who we are.
A coded version of ourselves that creates basically this ledger, a constantly evolving digital version of ourselves. But it isn't just that they have this thing. The narrator of the video goes on to say that this ledger of ourselves can actually be directed toward a goal.
What if the ledger could be given a volition or purpose, rather than simply acting as an historical reference? What if we focused on creating a richer ledger by introducing more sources of information? What if we thought of ourselves not as the owners of this information, but as custodians, transient carriers, or caretakers?
And then they break it up into these parts. Part 1 is an Italian phrase that I will likely butcher, but what it means is talking cricket. So part 1 is basically Jiminy Cricket. So part 1 is your conscience.
Initially, the notion of a goal-oriented ledger may be user-driven. As an organization, Google would be responsible for offering suitable targets for a user's ledger. Whilst the notion of a global good is problematic, topics would likely focus on health or environmental impact to reflect Google's values as an organization. Once the user selects a volition for their ledger, every interaction may be compared to a series of parallel options. If one of these options allows the ledger to move closer to its goal, it will be offered up to the user. Over time, by selecting these options, the user's behavior may be modified and the ledger moves closer to its target.
The narrator goes on to say, initially, This process will be user-driven.
Initially, the notion of a goal-oriented ledger may be user-driven.
But I feel like that bears repeating, that he said initially. Initially, it's user-driven, which by virtue of the fact that he says initially suggests that at some point it won't be user-driven. And so your options will still reflect Google's values, not necessarily the user's values, mind you. A person can choose a goal within the given parameters of Google's values, and the technology on the phone will then use every available bit of data to steer a person towards whatever that goal is. A process that over time will likely become so constant and so seamlessly integrated with all of the person's shopping and communication, social interactions with their phone, places they go, things that they do, etc., that the person's probably not even going to notice anymore that their behavior is now being continuously modified through the feedback loop of this technology. Cybernetics, as coined by Norbert Wiener back in the late 40s, was about communication and control in the animal and the machine. And it requires a feedback loop. So for this behavior modification feedback loop system to work, it's going to require more and more data to continuously modify the person's behavior.